Hi class, welcome again to another session on digital principles in system design. So we have been discussing the analysis procedure for an asynchronous circuit and we are going to discuss the transition table method. So let us consider this example where you have a combination circuit that has two NOT gates, three AND gates and two OR gates and there's a feedback mechanism in it. The circuit does not have any memory element in it, it's just a gated circuit. However, it has feedback loop and that's why it is a asynchronous circuit. Now this circuit diagram was taken from Morris Manners' third edition in the chapter 9. So let us take a pointer out and first of all see how this circuit is going to work. Now you have first of all you have to identify how many loops are there. So I have loop 1 here and loop 2 here, right? And then I have two excitation variables. So excitation variable, let me just repeat. So you have your x, which is your input. You have your small y, which is your secondary variable, or your present state, or your feedback, whatever you want to say. And you have capital Y, which is your output, also called as the excitation variable or the next state, right? So since I have two loops here, I have y1 and y2 as my two outputs. I have small y1 and small y2 as the two feedbacks or two secondary variables, and I have an x, which is my input. Now, first step is to identify the loops. The second step is to consider all these secondary variables as an input and then write a Boolean function for y1 and y2. So what will be y1? First of all, let us see what is going to be the input for this AND gate. Let me just call this number 1, number 2, and number 3. This is 1 and 2. Right? So this AND gate, here it is receiving y1 and here it is receiving x. So the output would be x, y, excuse my handwriting, I write better than this under normal circumstances. So x is the input coming to this NOT gate. So this AND gate is receiving x dash and this input is y2. So output of AND gate 2 is x dash y2. And this is y here, y1. So this is y1 dash, right? And this is x, so it's my x. So the output of AND gate 3 is x, y2 dash. Now if you see OR gate 1, it is receiving x dash y2 and x y1. So OR gate is just the summation of the two inputs. Therefore, Therefore, y1 is summation of these two inputs, so that is x y1 plus x dash y2. And my y2 is nothing but x dash y2, so this is y1 plus x y1 dash. Right? So this is the analysis that we do. So we have derived the Boolean expression for both y1 and y2 here. Now, so we have the circuit that has input x and two excitation variables y1 and y2 and two secondary variables y1 and y2, small y1 and small y2. So we have to calculate the delay induced by each by calculating the propagation delay between y and corresponding y. So each logic gate actually induces a delay of 2 to 10 microseconds and the y induces approximately 1 nanosecond. Sorry, 2 to 10 nanoseconds. So exact delay induced or approximate delay induced by each of the logic gates will probably be available in the data sheet. So you have to refer to that, right, while you are constructing the circuit. So this delay induced by the circuit is sufficient for the feedback to function properly and therefore we do not require any additional gate, right? So we have found out the expressions for y1 and y2, right, which was x y1, y1 was x y1 plus x dash y2 and y2 was x y1 dash plus x dash y2. Now the next step is to write y1 and y2 in terms of the minterms. So I have written that. And finally, voila, I have the K-map here. So I have populated the K-map for both y1 and y2. And then, I have to, from this I have to construct the transition map. Now, in order to do the transition map, I just write the two K-maps next to each other. And then, let us just say this is 1, 2, 0, 1, 3, 2, 4, 5, 7, 6. Right? This is how we write, right? 0, 1, 3, 2, 4, 5, 7, and 6. Right? So, in order to write the transition table from this K-map, all I have to do is I have to compare the 0 cells for both, and then take this 0 and write it next to this 0. So my first cell becomes 0, 0. Now in the fourth cell I have 0 here and 1 here. I just take this 1 and put it next to this 1. So it is 0, 1. Now here I have 1 and 1. I take this 1 and put it next to this 1, and so on. So you have 1 here, and I have again 1, 0 here. Then you have 1 here, which is also 1 there. So there's 1, and this 0 goes here. And then I have 1, 0, and then this 0 will come here to the second cell of the first K-map. Then you have 0, and then finally the 0 in the sixth cell of the second K-map goes to the one next to the 1 here. So this is how I write my transition table. So you just write two K-maps next to each other, and then construct the transition table accordingly. So now I have my transition table here. So in my earlier video I said that in order to analyze stability, my small y has to be equal to my capital Y. So in this scenario, my small y is y1, y2, and my capital Y is capital Y1, capital Y2. So the elements in each of the cell are the capital Y, and the elements here, that is 0, 0, 0, 1, 1, 0, and 1. Oh, sorry, 1, 1 and 1, 0. What am I writing? 1, 0, right? And then you have 0 and 1. So the idea is that the system would be stable when this cell equals to this value of y1 and y2. Now let us consider our first input where my x is 0, right? My y1, y2 is 0, 0, right? So that is my 0th cell here. So here I can see that this value and the circled value are equal. Therefore, when x is 0 and y1, y2 are 0, my system is stable. However, when I change x to 1, right? So when my x is 1, remember I can allow only one input variable to change. So my y1 and y2 is considered as an input for analysis procedure. We know that it is a feedback, but for analysis we are considering it as an input, right? So I am changing x1, xs. So where did x1 come from? So this is x as 1. So I'm taking my y1, y2 as 0 itself, 0, 0, right? So I come to this cell, which is the fourth cell. Here, if I see, my capital Y and small y are not equal. So my system is temporarily unstable. So in order to bring it to stable, I just change the value of y2, right? So if x is 1, y1, y2 is 0, 1, I enter this fifth cell, right? So this value and this value concur. So the system has entered stable. Now, system has entered stability. Now I don't like this, right? I just like to keep on changing my input. So now when y1, y2 is 0, 1, and if my x becomes 0 again, right? If x is 0, and y1, y2 is the same, right? So I come to this cell, which is cell number 1. So y1, y2 becomes 1, 1. Now this again, small y and capital Y are not equal, right? So this system becomes unstable again, temporarily. So I have changed my x in the last one. So I can, instead of changing x here, I'm changing the value of y1. So my y1, if I check my y, initially my y1 y2 was 0 1, right? If I change my y1 from 0 to 1, my y1 y2 or my small y becomes 1 1, which is same as the cell number 3, right? So this system again becomes stable. Now again, as usual, I just want to test my system further, and I'm making my x is equal to 1. So I enter this 7th cell. Now this is my capital Y and this is my small y, which are not equal. So my system doesn't like it. So what it does, it is changing the value of y2 again. So y2 becomes 0 from 1, and then I have the same x value, and this is my cell number 6, right? So again, during my cell number 6, my capital Y and small y are equal, and that's when my system becomes stable. So we can see here that every alternating value of x, my system becomes stable. So initially starting off when my x was 0, my system was stable, and then when x was 1, changing y1 and y2, my system became stable, and then again changing y1 and y2, my system became stable when x is 0 and x is 1 in the next row. So alternating x and x values, my system is stable for y1 y2 being 0 0 0 1 1 1 and 1 0, right? So another major difference between synchronous and asynchronous circuit is that in synchronous circuit the output changes only in presence of the clock signal. However, in asynchronous circuit the output changes as soon as the input changes. So if you have combined secondary inputs, right? If you combine your secondary input and the input provided by the external input provided, then this whole information is called as the total state. So therefore, for total states 0 0 0, 0 1 1, 1 1 0 and 1 0 1, your system is stable and our circuit was stable. And for total states 0 0 1, 0 1 0, 0 1 0 0 and 1 1 1, my system was unstable. So if I want to write a transition table that is similar to the state table, I just take the small y values, which is my present state, and the capital Y values when x is equal to 0 and capital Y values when x is equal to 1 as my next state, and I tabulate it, and I can rewrite my transition K-map or transition table as a state table this way. Finally, to summarize the design steps, so first of all I need to determine how many feedback loops are there, and second I need to find out the capital Y and the corresponding feedback small y. I have to consider small y as an input along with the external input and derive a Boolean function for all the capital Y's available. Then I have to plot the K-map and then combine all the K-map into one table, which is the transition table, and circle the squares where small y and capital Y are equal, and then finally analyze how my circuit is behaving. So this is how I'll do an analysis of a combinational circuit using logic gates. I hope you had a very fruitful session learning about this with me. I shall see you again in another video. I hope you take care till then.